6,000 tweets per second, 500 million tweets a day, and 200 billion tweets a year. That is the sheer volume of data being processed at Twitter, now known as X, on a daily basis. And with so many tweets flying around, how do the people at Twitter figure out which ones are some motivational quotes and which ones are targeting someone with negative political rants? Hello everyone and welcome back to my YouTube channel. I am Selina, and in this week's video, we are going to discuss the intuition behind naive Bayes, a smart but simple algorithm that works behind the scenes of popular applications like Twitter and Gmail to help process huge amount of data continuously. We will start by learning about the history and definition of naive Bayes and move further to understand the Bayes theorem using a data set, and then ask more and more complex questions to understand the topic better. And finally, we will conclude with an implementation of naive Bayes in Python. So let's dive in. The naive Bayes algorithm is rooted in the fields of probability and statistics, and it dates back to mid-18th century, where it was developed by Thomas Bayes, an English mathematician and Presbyterian minister. It was reintroduced in the 1960s and 70s for classification tasks, and finally in 1990s it became super popular in machine learning, especially for natural language processing related tasks. But why is our Bayes algorithm called naive? Like, what is the reason behind it? Well, it is called naive because it assumes that all the factors that are affecting our prediction are independent of each other. They are in no way related to each other. So let us understand this with a simple example. Let us say you want to predict whether it is going to rain outside today or not. And there are three factors that you can think of. One is the weather cloudy today? Does it look like it is going to rain? The second thing is the ground already wet? And the third factor is, what did the person in the weather forecast on TV say today? So according to you, which is a real life person in this real life scenario, all these three things must be correlated. If it is cloudy today, then the ground might be wet or something like that. But then in case of naive Bayes, the algorithm is so simplified that it assumes that all these three things are not related to each other. That if it is cloudy, it has nothing to do with the ground being wet or whatever the person on the TV says. That is why it is called naive. Why is this naive assumption useful for us? Well, because it is so naive that it is assuming that all the factors are independent, we don't have to worry about any cross relations. And that is why the algorithm becomes so fast and so accurate in many situations. Let us now understand the naive Bayes theorem with the help of a data set. Let us now understand the maths behind the naive Bayes theorem using this simple data set, wherein we have to predict if we can play tennis or not based on the weather conditions. The four factors that we have taken here are the outlook of the sky, the temperature on that given day, the humidity, and the wind condition. And now we have to predict whether we can play tennis or not based on these four independent features. We want to predict whether tennis will be played on a new day with the following conditions. So we are given these four conditions to test our data on. The first one is that the outlook should be sunny, the temperature should be cool, the humidity should be high, and finally the wind speed should be strong. Let us see. From our data set, we know that the total number of records that we have is 14. That is, the number of values or yes or no or our data entries is 14, out of which the times that tennis is played is 9. That is, 9 out of the 14 records say yes, we do play tennis. And 5 out of the 14 records say that no, tennis will not be played. So the priors are the probability of yes is 9 out of 14, that is 64%. And the probability of no, that is you cannot play tennis on a given day, is 5 out of 14 or 36%. Let us now find out what is the likelihood for yes and the likelihood for no. That is, what is the probability that it will be sunny, given that we already know that yes, we can play tennis. The probability that it was cool that day given that we already know that we can play tennis, and similarly for the others. So, first, let us look at the probability of it being sunny given that it is yes, we do play tennis. Over here, you can see that all the denominators are 9. Now, why are they 9? It is because we are looking for the likelihood of yes. That is, the number of times it was sunny, given that we know that on 9 days, yes, it was. You can play tennis. Let us go back to the data set. Here you can see out of the 9 yeses, there are only 2 rows in which we have sunny condition, and hence we take 2 out of 9. Now that we come back here, we can clearly understand that for cool it was 3 out of 9, high humidity 3 out of 9, and strong wind 3 out of 9. Similarly, we can find the likelihood of no. That is, given that it was sunny, whether it was no, we cannot play tennis. And similarly for the others. Here we have taken the denominator 5 because we have only 5 cases where there is play tennis no. Let us now move further. Finally, we come to the posterior calculation for yes. Over here, we multiply all the individual likelihood probabilities with the complete probability of playing tennis, and we get the value 0.0038. And in the case of no, we get the value of 0.0207. And since the probability of no is greater than the probability of yes, play tennis equals no is predicted. There are three types of naive Bayes algorithms. The first one is Gaussian naive Bayes, then there is multinomial naive Bayes, and the third one is Bernoulli naive Bayes. Let us start by discussing the Gaussian naive Bayes. Imagine you have a group of students and you want to predict whether they'll pass or fail based on how many hours they study. Here's the key idea. Gaussian naive Bayes assumes that this continuous data, that is study hours in this case, follows a bell-shaped curve, which is also known as a normal distribution. So if you were to plot study hours on a graph, you would get this nice smooth curve where most students fall in the middle and fewer students are at the extremes. It looks at this curve for each class, let's say pass or fail, and figures out two things. First one is the average, that is, how many hours do students typically study to pass, and the next one is the variance. How much do study habits vary for students who pass? Once Gaussian naive Bayes knows these numbers, it can estimate the probability that a new student will pass or fail based on where they fall on the curve. Next up is multinomial naive Bayes, which is used for discrete data or the data in which there are things that you can count. Suppose the count of the number of times a word appears in a document. This is especially used in text classification tasks. Let us look at these examples here. In the spam email example, don't miss out on this limited time offer. Click here to claim your free gift now. And in the non spam email, let's schedule a meeting next week to discuss the project updates and review the timeline. Over here, we can see that words like limited, offer, and free are there in the spam email, and a word like meeting is present in the non spam email. Then, when a new email comes in, multinomial naive Bayes adds up the likelihood of each word being in either category. And based on that, it makes a prediction. Is this email spam or not spam? Bernoulli naive Bayes only deals with Boolean data. That is, it only cares if a feature is present or not. That is 1 or 0. It is like a light switch, either on or off. Once again, let us look at an example. Let's say you are checking emails for the word discount. Now, Bernoulli naive Bayes will simply ask, is the word discount in this email? It doesn't care about how many times it shows up. It just wants to know if it's there or not. So, if discount is present, like over here you can see, you get a yes. Look, it is present and 1. If it's absent, then you would have got a no. This model estimates the probability of each feature being present or absent for each class, spam or not spam. Let us now look at a code example to understand the implementation of naive Bayes in Python using scikit-learn and machine learning. To understand the implementation of the naive Bayes algorithm, I have made use of the iris dataset, which gives information about the measurement of different flowers, namely Setosa, versicolor, and virginica. We start by importing the load iris or the dataset from sklearn.datasets. Then we import the train test split function from sklearn.module selection to split our dataset. And next, our model, that is Gaussian naive Bayes, and then our metrics that we will be using to testing the training model, that is accuracy score and classification report. So our first step is to load the dataset. X contains the data and Y contains the target or the prediction. Next, we split our data set using train test split. We split it into two parts. 80% of it is training data and 20% is testing data. Next, we use this function to create the model and then model.fit to fit the model on our training data, that is xtrain and ytrain, where xtrain are the independent features and ytrain is the prediction. Next, we come to ypred, which predicts the value of the prediction for each value of the testing value. We can see that we have got an accuracy of 100%. And once you go down to the classification report, you can see a more detailed overview. Now we come down, we can see that the actual flower was versicolor and the predicted one was also versicolor. This has done for a certain test data. Over here, you can see all the actual and predicted data. At the end, we can visualize how these features are related to each other. Like if you see the sepal length versus the sepal width, you can see that there is no clear division or separation. But if you come to petal length versus petal width, you can see that the petal length increases, then so does the petal width. And over here, as the petal length decreases, then so does the petal width, as is in the case of setosa. The last matrix that we see is the confusion matrix. It tells us that for every actual prediction that was supposed to be done, what was actually predicted. Like over here, actually we were supposed to get setosa. How many times did we get setosa? All 10 times. And then how many times did we get versicolor? 0 times. And how many times did we predict virginica given that it was setosa? Again 0 times. This means that every single time the model was supposed to predict setosa, it has predicted setosa. Similarly for versicolor and also for virginica, which gives it its 100% accuracy. That is all for this week's video. I hope you enjoyed it and got to learn something new today. And if you did, then don't forget to like, share, and subscribe. I'll be back next week with another intuition behind another machine learning algorithm. Till then, thank you for watching and see you again in the next video.